Okay, hi guys. Let's do the check you understand on page 365. All right, for each random process given, determine whether the events are independent. Okay, so independent means knowing one event happened does not influence the other event. Okay, so we're going to shuffle a standard deck of cards and turn over the top card. Put it back in the deck, shuffle again, and turn over the top card. Define event A as the first card is a heart and the second card is a heart. Okay, so when I think of a series of events, I usually think of a tree. So I know this is a lot to think through this question, but it's nice to visualize. Okay, so my first branch of my tree is going to be my first card. It's either going to be a heart or not a heart. That's my heart. Okay, what's the probability the card's a heart? Well, a quarter of the deck is a heart. So there's 13 hearts out of a deck of 52. Okay, so not a heart is just the rest of them. So what's that? 39 out of 52. Okay, so there's a 13 out of 52% chance, or 0.25 0.25 probability that I'd get a heart. It's a quarter of the deck. Now, if I put the card back, okay, I still have 52 cards. So my second card, whether it's a heart or not, is the same probability because I put the cards back. Okay. So these events are independent because since I put the card back, it doesn't matter whether I got a heart from the first time or not, because the probability of getting a heart the second time is the same. Okay, it doesn't matter what the first card was, whether it was a heart or not. Probability of getting a heart the second time is going to be the same because I put the cards back. So these are independent. These are independent events. Okay? Now for the second one, it says, shuffle a deck of cards and turn over the top two cards one at a time. Okay? And we'll see if the first card's a heart and the second card's a heart. So now this one, there is no putting the cards back. So card number one is either going to be a heart or not. Same probability when I start off. Okay, there's about a 1/4 chance it's going to be a heart, 3/4 chance it's not going to be a heart. But the second card, put a little line here. Oops. Now, if the first card was a heart, I'm going to have one less heart. As a matter of fact, I'm going to have one less card too. So the probability the second card's a heart is only 12 out of 51. Okay, so these are dependent because whether that one's going to be a heart depends on whether this one's a heart. Okay, now if the first one was a heart, the probability the second one's not a heart, I still have all 39 non-hearts, but I have one less card. Okay, now the second card being a heart, if the first one was not a heart, okay, so I still have all my hearts, but I have one less card. So again, probabilities are different, okay? And of course this is not, so I have one less not heart card and one less card. Okay, so the fact that this probability depends on what happened here, all these probabilities depend on which one we chose here. These are not independent. Okay, so these events are not independent. I'm drawing two cards at one time. Okay? All right, let's look at the third. The 28 students in Mr. Tabor's AP Statistics class took a quiz on conditional probability and independence. The two-way table summarizes the class quiz's results based on gender and whether the student got an A. Choose a student from the class at random, and let's see if the events of being female and getting an A are independent. Okay, so we have got an A, yes or no, whether they're female or male. Okay, so I'm going to do this a little more formally. So we learned in our formulas to prove independence, if the probability of A, given that B has already occurred, equals the probability of A, then the events are independent because it means the probability of A is going to be the same no matter whether B occurred or not. Okay, so in this case, we'll take event A as got an A, and we'll use event B as being female. okay? So I want to see if the probability that a person got an A given that they're female is equal to the probability that somebody got an A. Okay, so in order to do my conditional, I'm going to say of all the females, so 18, 19, 20, 21, what proportion got an A? All right, well, 3 of them did. Okay, so what's 3 out of 21? I don't know, 0.143. Is that the same probability? Is that the same probability of getting an A? Okay, so I know there's 28 students, right? I know there's 28 students. So of the 28, how many got an A? So it looks like 4, right? 4 out of 28. Well, 4 out of 28 is the same proportion. Whoops. Okay, they're both 1/7. So these are equal. These probabilities are equal. So that means these two events, getting an A and being female, are independent, okay, because those probabilities are equal. Okay, now I want to go a little further and talk about this, okay, because we've seen this concept of independence in chapter 1 when we did conditional distributions. Okay, so if we think about this as a conditional distribution, I'll do it real quick. Okay, if I think about this as a conditional distribution, I'm going to summarize, I'm going to do all my conditional distributions per gender. Okay, so we have male, female, and male. We have got an A and did not get an A. Okay, I'll put an A with a question mark. So of all the females, that's 21, right? 3 got an A, 18 did not. Of all the males, which is 7, 1 got an A and 6 did not. So 3 out of 21 we just figured out is 143, and so is 1/7. Okay? 18 out of 21 is 6/7. Okay, so these are also the same conditional distribution. So if we think about it in terms of our segmented bar graph, right? These are all my males. Oh, I should have switched it, whatever. Okay, so we got an A, yes or no. We'll do those like that. So females that got an A, it's 14%, so that's like that. Males that got an A is 14%, so if they got an A, we did this. And if they did not get an A, we'll do these lines, okay? So these distributions are exactly the same, okay? So remember from chapter 1, we said different equals dependent. Well, the same equals independent, okay? So this matches my proof using probability, okay? No matter how I prove it, my events are independent, okay? Put a little asterisk right there, because they're the same. Okay, I hope this was helpful, and I'll see you next time.